Okay, everyone, welcome back to the Intro to Machine Learning. So today's lecture is going to be about the unsupervised learning. We're going to continue from there on, but I do see that there are only 12 participants at the moment. So we're going to wait another 2 or 3 minutes in order for more students to join. One thing we know is that since we set the password, a lot of you, including myself, actually, a lot of us are struggling to join the Zoom meeting as quickly as we used to. However, in a minute or two, hopefully everyone will be able to join us. And as usual, this lecture is being recorded and will be uploaded to the NYU stream after the lecture is done. So because Zoom is been growing so much and then their user base is growing, what happens is that their cloud recording has started to lag a bit in the sense that it takes longer for them to pre-process or the post-process the video recording and for me to download. And also the NYU stream started to lag behind because their user base is growing as well. So the post-processing of the video recordings is generally taking longer. So please be patient and then wait at least a day before checking in to see if the video recording has been uploaded and the link has been shared on CampusWire. And as usual, if you have any questions, please do use the Zoom group chat to ask the question, and then I'll try to answer that as I go through. And today's lecture is going to be filled with all those equations. So I'm pretty sure there are not going to be that many questions. However, if you have any, just do let me know. So let's wait another minute or two. So we have 14 participants at the moment. All right, 15 participants. All right, anyway, we can't wait too long because we got a lot of materials to cover today. So last week we learned about, what did we learn about? Mixture of Gaussians. And then what was the mixture of Gaussian? Mixture of Gaussian was the generalization or the extension of the k-means clustering that we learned. So what we learned back then was the k-means clustering first. And then we extended it into the mixture of Gaussian. And we talked about what mixture of Gaussians can do in the lab session last week. K-means clustering can only model the clusters to have a same shape. On the other hand, with mixture of Gaussian, you saw already in the lab session last week that the shapes of each clusters can vary because we can model the covariance matrix of each Gaussian component separately from all the other components. And then that allows the mixture of Gaussian to do a clustering in a much more flexible way. But then today, what we want to look at is so-called hidden Markov model. One thing that was lacking from the mixture of Gaussian was the fact that each and every data point that we're going to cluster into or they assign into one of the clusters was independent from all the other data points. However, that's not necessarily true. If I wanted to do some kind of clustering of a music so that each and every frame in the music is going to belong to one of the potential instruments or one of the potential theme underlies the music, then what I want to take into account is not only individual frames, but also how that frame is in relationship with other frames. That is, I want to be able to cluster data points based on the context in which it appears. So up until mixture of Gaussian, each data point is a single point that is independent from all the other points. But this is very, very limiting. What we want is that we want to be able to use a time series or a sequence. What if each and every data point? Can you please share the notebook? Can't you not see the notebook that is being shared? Okay, Carol can see it. Katrina, can you? Okay, Ilya can see it. Okay, so Katrina, maybe you could exit and rejoin the Zoom meeting, and then probably it's going to show you. Okay, all right, perfect, thank you. So what we want is that we now want to look at a sequence instead of individual data points. And then why is it important? Let's think about a word or a sentence. Now you can think about clustering each and every word into, cluster all the unique words into a small number of categories. And in that case, we might have words that are nouns. So there could be a noun cluster. And then we could have words that are verbs. And then there's a verb cluster. But once you start thinking along this line, then you notice that this cannot be perfect. Some of the words can be used both as verbs and nouns. In that case, how will we actually tell whether the word belongs to the verb or noun cluster? It turned out that it's actually relatively easy, or in fact, quite straightforward for us, the language users, humans, to decide which cluster the word belongs to if we knew in which context or in which sentence the word appears. And then what we want with this hidden Markov model is to extend the mixture of Gaussian so that we not only look at an individual word or the individual instance, but we also look at in which context that individual word or instance appears. So what it means is that earlier, what we did was to think about X as the input and then Z as the cluster assignment. So this is what we thought about. However, now we are going to change it so that the input is going to go from the X0, X1, all the way to XT. In fact, I'm sorry about that. We don't need the X0. So our input is now going to be a sequence. So you can think of the word, or you can think about the audio, you can think about the stock market, whatever you think about, there are tons of time series in the word. So instead of looking at a single instance, we're going to look at a time series or a sequence of instances, and then the sequence is going to be a single instance for us in this hidden Markov model. And then of course, accordingly, we are going to have a sequence of cluster assignment. Z1, well, in this case, we're going to start with the Z0, Z0, Z1, Z2, all the way to ZT. So now we're thinking about a sequence instead of a single data instance. And as we learned last week at the mixture of Gaussian, what we're going to do is we're going to build a probabilistic graphical model, or the probabilistic model of this hidden Markov model, or I prefer to call it a temporal extension of the mixture of Gaussian. Now, what are the things that we need? Considering having this sequence of random variables, so all these variables are random variables, right? Z0, Z1, all the way to ZT, and then X1, X2, all the way to XT, they are also random variables. Then in order to build a probabilistic model out of it, first we need to have a prior distribution. Now, first prior distribution we're going to have is the P of Z, Z0. So Z0 corresponds to not observing anything. It's just a sequence. So let's try to draw a graphical illustration of what this model looks like. We're going to have Z0, that is the first random variable. And then given that Z0, we want to decide what the cluster assignment of the first observation is going to be, that is the Z1. And then given that cluster assignment, we want to now observe the corresponding observation. Now, if we only had Z1 and X1 here, then that's going to be a usual mixture of Gaussians. However, now we have the temporal connection here that tells us that the assignment of the first cluster is dependent upon the assignment of the previous cluster. And then now we can just continue doing so by telling that the assignment of the second cluster is dependent upon the assignment of the first cluster. Now, important thing is that it's only dependent upon the first cluster assignment, not the 0th cluster assignment. And then this is why we call it Markov model, because the choice of the cluster assignment at time step t only depends on the choice of the cluster assignment at time step 1. And then it does not care about anything before. So it is in fact memoryless. And then now given the second cluster assignment, we have the observation at time step 2. And then we continue to do so until we look at the cluster assignment of the tth step, that is the last step, and then we look at the observation. And to do so, we need to first look at what is the prior distribution over Z0. And then this prior distribution is going to be a categorical distribution where the parameters or the probabilities over all possible k many states are simply mu 1, 0 all the way to mu k 0. Now the superscript 0 refers to the fact that this is the parameter or the probability at the 0th step, that is Z0. And then we have the subscript 1 all the way to k, meaning that there are k many clusters. So in many other literatures, they also call it states, but states, clusters, all the same thing at the end of the day. And then clusters are more informative in this case because it actually tells us that there are k discrete states. But on the other hand, states could very well be continuous as well. Let me see. Okay, I'll just try to mute all of you. Okay. All right, let's continue. So that was the first prior distribution. And then looking at this graphical illustration of the hidden Markov model, and then if you're trying to make analogy to the mixture of Gaussian that we have learned, what is the second thing we need to define in terms of the probability distributions? The second thing is what happens to the cluster assignment at time step 1 given cluster assignment at time step 0. So we need to look at each and every directed edges, and the second directed edge we want to look at is the transition dynamics or the transition edges. And the interesting thing about the hidden Markov model is that this model should work with a sequence of any length. That is, this t here needs to be any positive integer. Could be 1, could be 2, could be 100. What it means is that we cannot really afford to have these conditional distributions corresponding to these transition dynamics to vary from one step to another, and then that transition has to be shared across time. That is, these transitions all are shared. And how are we going to share them? We are going to simply define it as the probability distribution over ZT, the cluster assignment at time step t, given cluster assignment at time step t minus 1, that is ZT minus 1. And this again is going to be categorical distribution. However, these probabilities will be dependent upon the value or the cluster assignment of the t minus 1 step. So how we are going to write it is that the mu1, so the probability of ZT being the first cluster 1, is going to be mu1 ZT minus 1. Now ZT minus 1 could take one of the k many values, and then there's a mu1, and then there should be k many mu1s. Right? And what it means is that this whole distribution here, or this conditional distribution or the transition distribution, can be fully described by having a large table And then the number of entries in the table is going to be k times k minus 1 divided by 2. In fact, that's not true. It should be just k squared, right? So you can go from first cluster to the first cluster to the second cluster, and all the way to the kth cluster to the kth cluster. So we're going to have the k squared many entries in this table, and then that's going to tell us about this transition dynamics. Now looking at this, we have defined the prior distribution over Z0. We have defined this transition distributions that is going to be shared across time. And what is the last remaining thing? We need to now define the so-called emission distribution or the observation distribution. And then again, similarly to what we talked about with the transition dynamics or the transition distributions, these distributions or the emission distributions are shared across all those time. And then that is how we actually build a hidden Markov model to work with any length sequence. So let's try to write it down. So that's going to be P of xt given zt. And then as we are extending the mixture of Gaussians, we are going to say that this emission distribution, that is a probability distribution over xt given zt, that is a cluster assignment at times of t, is a Gaussian distribution. It follows a Gaussian distribution. And in order to make things a bit simpler, we're going to say it has a diagonal covariance. Although, as you learned last week, that it's not really difficult to extend whatever we have derived using a diagonal covariance into having, identity covariance. Identity covariance into having diagonal covariance or even a full covariance if you have enough data points. Now, in this case, how we parameterize this Gaussian distribution is to have the mean of the Gaussian distribution dependent upon the choice of the cluster, that is a ZT. And then there are k many values that ZT can take. What it means is that we effectively have k many Gaussian distributions here. Makes sense. That's just like what the mixture of Gaussian was. So if we didn't have this transition dynamics, then, and looking only at the prior distribution over Z0, and then forgetting about the subscript that indicates the time, and then looking at this emission distribution, again, without considering these subscripts that indicates time, then we end up with a mixture of Gaussian. However, this transition dynamics, in fact, gives us amazing power to model way to model a sequence of observation instead of independent observations. Now, once we have all these base distributions, then we can now rewrite the joint distribution. As we learned last week when we were talking about the mixture of Gaussians, joint distribution really tells us essentially everything we need to know. So log P of x1, x2, all the way to xt, and then z0, z1, all the way to zt can be written. So we're always working the log domain, right? So that's much easier to write down. And then that actually separates out the numerator from denominator of the probability distributions. And then we never want to have fractions. So it's always a good idea. Then what we end up with is that first we have the Gaussian distribution with the identity covariance. You now see, why I always work with identity covariance, at least in the lectures, because that makes the derivation so much straightforward. So we're going to go through each time step and then look at the difference between what is predicted based on the choice of the cluster ZT and what we have actually observed, that is the XT. And then we look at the Euclidean distance between these two. And we have the log probability of what ZT should be. So given Z0, not Z, but 0, 0. So given the configuration of Z0, what is the log probability of that Z0? And then we already know from the prior distribution that the probabilities of the configurations of the Z0 are simply given by these mu parameters. So that corresponds to this term, the second term here. And then we have plus sum over t. Now, why do we need another sum over t? That's because we need to consider now the transition. So first two terms are identical to the terms from the joint probability of a mixture of Gaussians from last week. However, because of this transition that tells us about the relationship across time, we now have the third term that tells us about the probability of the cluster assignment at time step t given the cluster assignment at time step t minus 1. And of course, we are going to have some constant term there that comes from the denominators. That is the normalization constant of all these distribution. Gaussian distribution, because our covariance is identity, the denominator is simply going to be square root of 2 pi times 1. So we don't really care about that because that really doesn't tell us anything. And categorical distributions are just categorical distributions, so no additional normalization constant shows up. Now, once you do some derivation and then put things together, I won't have time to go through them all together. We can end up with a bit simplified form, or the form that's going to allow us to derive all the other things more simply. And then there is a sum over t, and then we're going to go through each and every cluster. So we're going to indicate it with a lowercase k. So it goes from 1 to capital K. Then here's the indicator function. We want to see if the ZT is K. So we're going to try all possible clusters going from 1 to K. And then at each time step T, we want to see if the cluster assignment or the cluster was assigned to any one of them. And then this indicator function here, in fact, tells us about this. Times minus 1 over 2 xt minus mk squared plus sum. Now we're going to introduce another cluster assignment index, so k prime. And then we're now going to look at whether the zt minus 1 was k prime, right? Because we need to consider all possible ways in which the previous zt minus 1 cluster assignment change it, or the transition to the zt. So we need to have a double summation here. And then we look at log mu k of k prime plus the sum over k. Now this, we're looking only at the clusters. Why is that? Because we're going to now look at the z0, which does not depend on anything before. So z0 doesn't really depend on any previous time steps. The z0 is the end of everything. So we'll see whether z0 belongs to the kth cluster, and then we say that, okay, that should be multiplied with the log of the mu k 0. So this is how we are going to write the joint distribution, joint probability of x1, xt, and z0 to zt. Now, once we have this joint distribution, okay, so there's a question from Carol. Does log mu k prime need to be conditional on k? Yeah, that's actually true. And then it is conditional because we do have the subscript k here. So mu k of k prime is the probability of zt belonging to k given, well, hold on. Yes, zt belonging to k given that the zt minus 1 was k prime. So it is conditioned on k already. So once we have this joint distribution, and then we know that this HMM is an extension of the mixture of Gaussian, we can now think about what we should do in order to fit this hidden Markov model on the actual data. And then what does it mean to fit the hidden Markov model or train this hidden Markov model on the data is to figure out what this mu01 to mu0k should be. And then also what the mu k of k prime should be. So we have a very large table there. And also to figure out what this means of the Gaussian components. So that is the m of zt should be. So we need to figure that out by looking at all those data points. And then in order to do so, what was the algorithm that we discussed last week was the expectation maximization algorithm. And then we're going to use how we can apply the expectation maximization on HMM now. And then if you remember from the last week's discussion, expectation maximization algorithm, the first thing that we need to do is to figure out the posterior distributions over the unobserved variables, where the unobserved variables last week as well as this week correspond to the cluster assignment. So we only see the data points, observed data points. However, we do not see to which cluster they belong to. If we knew that, that's going to simply become supervised learning, and then that becomes a classification problem. However, in our case, that's not the case. What we have now is only the observations, and then each observation in this case is a sequence, and then we have a sequence of cluster assignment that is Z0 to ZT, and now we need to compute the posterior distribution over each and every Z0 to ZT. So in other words, we need to compute ZT1 given X1 all the way to XT. So this is what we need to compute. This is the posterior over ZT, given the observation sequence X1 to XT. Once we know this, we should be able to estimate. What should we be able to estimate? We should be able to estimate the parameters of this emission distribution, because this conditional distribution depends only on ZT. So all we need is the posterior over this ZT, and then we can compute this. So let's look at how the posterior over ZT looks like. So in order to do so, we look at all the terms in this joint probability, log joint probability that has anything to do with ZT. So looking at the joint probability here, I see that, okay, ZT appears here, and then ZT does not appear here, so we don't really care about that. And then ZT is going to appear here as well in the next time step. So if I were to write it down again, what's the time we have? It's 11:27. So I can write this down, log P of ZT given X1 all the way to XT as some constant, because we are looking at the log space, and then all we need to care about is what are the terms that depend on this ZT, and then anything else is going to work as a constant. And then what does that constant correspond to? That constant corresponds to the normalization constant that makes this distribution or the probability sum to 1. And in this case, what we end up with is plus minus 1/2 xt minus mk. Wait, I think I actually deleted something. Yes, okay. So let me actually rewrite one quick thing, saying that because, you know, writing down ZT over and over is not that convenient. So what I'm going to do is I'm going to simply say that we are looking at the log posterior probability of ZT being K. Then I can simply use K instead of the ZT over and over. That just makes it much cleaner. So squared plus, now I'm going to look at all the possible clusters to which the ZT minus 1 was set to. So it's going to be ZT minus 1 equals K prime, and then log mu K, K prime, and then plus K prime again, and then ZT minus plus 1 equals K prime, and then we have the minus 1/2 xt plus minus mk prime squared plus log of mu k prime and k. Now we have these three terms, but of course we don't care about this constant term. Now let's look at this second term only. What we see is that this first term within this second term tells us about how likely our observation at time step t is according to our choice of the cluster k. Because this essentially tells us, now given the cluster assignment k, now what is our prediction of what the observation should be? That's mk. And then we're trying to look at how mk is different from xt, our actual observation. And then the second term is the prior term, right? So how likely is this K assignment without looking at the actual observation xt? Now, this prior turned out, in fact, very interestingly, that depend on the zt minus 1. That is, our prior of the cluster assignment at time step t, that is zt, depends on what zt minus 1 was. So this actually tells us about the dependency structure in the prior. Now, what is then this third term? This third term, in fact, looks at the next time step. Because the choice of the cluster at time step t influences the choice of the cluster at time step t plus 1, we now have this third term that tells us if the cluster assignment at time step t was k, then how the cluster assignment at t plus 1 changes, and then thereby changes how likely our observation at time step t plus 1 is. So this right-hand side, these two terms, except for the excluding the constant term, tells us about not only the observation, but how the choice of the cluster assignment at time step t influences the choice of the cluster at time step t minus 1, as well as time step at t plus 1. Now then, we can continue to write it further. And what we end up with is some constant minus 1 over 2 xt minus mk squared plus log of mu k zt minus 1 plus log of mu zt plus 1 zt plus 1. Let's just rewrite it. Zt plus 1 and then k. So the reason why we could write it down like this is that because we noticed that this how likely xt plus 1 is given z prime does not depend really on k at all. So we could in fact remove this. And then what we end up with is the first our emission, or the likelihood of observing xt given the cluster assignment k, and then how likely it is for us to observe k given that the zt minus 1 was k prime, and how likely it was to observe zt plus 1 to be k prime given k. So we end up with these three terms plus a normalization constant. And again, what we see is that this is identical to what we saw already in the mixture of Gaussian. On the other hand, these two terms are effectively telling us what the prior distribution should be on the cluster assignment at time step t, given the two adjacent neighboring time steps. That is zt minus 1 as well as zt plus 1. Now, what we are going to do is we're going to write down this in the usual probably, let me see. So this is, I'm sorry, actually, this is my mistake there. My bad, but it's okay. So here, so we want to look at the posterior. And then in order to look at the posterior, what we are going to do is we are going to look at what this distribution over the zt is from the joint distribution. And then what we end up looking at is that we realize that this is going to depend only on xt and zt minus 1 as well as zt plus 1. So why is that? Because it really depends on xt, and then it depends on zt minus 1, and then it depends on zt plus 1. Now the John has a question. Why does time t plus 1 affect the posterior time t? That's a great question, because looking at these equations only, it looks like zt should be influenced by zt minus 1 only. However, if you think about it, what this implies is that the zt plus 1 is going to be influenced by zt. That's why we cannot remove any future frames, and we need to look into the future as well. Changing zt minus 1 is going to change how the ZT2, ZT minus ZT, changing ZT is going to influence what ZT plus 1 could be. That's why we need to consider ZT plus 1 in order to tell what the probability or the posterior probability of ZT should be. So this is what we ended up. However, what we wanted was not this, right? What we wanted was to have a probability distribution over ZT given x1 to xt only, without any dependence on the other cluster assignment. What it means is that what we need to look at is to look at the P of ZT equals K given x1 to xt. And then how we're going to do so is to marginalize out ZT plus 1 and then ZT minus 1 from this distribution. And then how we're going to do that is to write it down as ZT probability of the ZT minus 1 given x1 to xt minus 1 times probability of ZT equals K given xt ZT minus 1 and then ZT plus 1 times the probability of ZT plus 1 xt plus 1 all the way to xt. Now this is a very interesting equation here. So this middle term, we already looked at it, we know how to compute that. But where does this left term and the right term comes from? Left term and the right term comes from the fact that once we observe, let's say Z1 here, or let's actually write one more thing there. That is, I'm going to introduce Z3, and then I'm going to say X3. Now the interesting thing here, which can be a bit confusing, is that if I observe Z2, so if I observe Z2, I know what Z2 should be, then the probability over Z1 now depends solely on X1. It's not going to change, the distribution over Z1 is not going to be influenced by all the future observation because now I know exactly what Z2 should be. Because of this Markovian property that is a memoryless property, once I know the state of ZT anywhere in the middle, then it breaks the chain or the dependence that goes beyond this variable, across this variable. And then what it means is that the equivalently probability over ZT plus 1 is now only going to depend on all the future observation and is independent of the past observation. And then that's where we get these two terms that are left and right. And sometimes we call it forward and backward. And in fact, that's exactly what we are going to do. We're going to call this alpha t minus 1. That's going to be the values that we're going to compute by going forward, right? So what do we mean by going forward? We go from the x1, x2, all the way to xt minus 1. And then while doing so, we compute the posterior distribution over zt plus minus z1 all the way to zt minus 1. And then we're going to do the same thing, but in a backward direction or the reverse direction using, and then we're going to call that beta plus 1. So we're going to have, all we need to do is, because we know how to compute this middle term in the middle, all we need is trying to figure out how to compute this alpha t minus 1 and beta t minus 1. So before we see this, let's look at one question from Carol. But there are two links for each zt minus 1 and zt plus 1. Why don't we need to consider the other link? There are two links, yes. So link here and then link there. And then we are actually considering this pair first and then that pair. And then that's why we end up with these three terms. So one is, so let's go back here. So what we need is that if you want to compute the distribution over ZT, we need to consider its connection from ZT minus 1. And then we need to consider its connection to ZT plus 1. And then its connection to XT. Then that's how we end up with these three terms. This term corresponds to the connection to xt, and then this term corresponds to the connection from zt minus 1, and then this term corresponds to our connection to zt plus 1. That's why we get these three links. So now, how are we going to compute this alpha t minus 1? let's try to write down probability of zt minus 1 given x1 all the way to xt minus 1. And then this can be rewritten as marginalizing out zt minus 2. That is, we're going to have the zt minus 1 given xt minus 1, and then zt minus 2 times zt minus 2 given x1 all the, all the way to zt minus 2. And then one thing you notice here is that now this and the second term look almost identical, except that the second term here on the right hand side, the second term in the right hand side is simply one step before the left hand side. So what it means is that this is in fact a recursive formulation. In other words, we wanted to compute alpha t minus 1 here, and alpha t minus 1 is a function of alpha t minus 2. And all we need to do is we need to figure out how to compute this first term in the summation on the right hand side. Let's try to write this down. So p of zt minus 1 given xt minus 1 and then zt minus 2, we can use the base rule again to rewrite it as the p of zt minus 1 given p of zt minus 1 given p of zt minus 2 times p of xt minus 1 given zt minus 1. Now, how did we get here from left hand side to the right hand side? It's just the application of the base rule and realizing that once I know what zt is, then the distribution over xt is fixed regardless of whatever the value zt minus 1 or the zt plus 1 to, because I know what the value of zt already is. Once you notice that, you end up with this equation, and then writing this down, that is writing log p of zt minus 1 given xt minus 1, zt minus 2, we end up with, let me see, some constant. We always have this normalization constant plus log of mu zt plus 1 minus 1, zt minus 1 of zt minus 2. I think it should be flipped, right? Yes, yes. Oh, no, this is correct. Zt minus 1 given zt minus 2. So this is going to correspond to the first term in the right-hand side, minus 1 over 2 m zt plus 1, zt minus 1. Oh, it's so confusing. Zt minus 1 minus xt minus 1. And then now we look at the squared. And then this corresponds to this emission or the log of the emission. Now we know how to compute this. Then what it means is that given this alpha t minus 2, which is going to be a vector, right? It tells me about alpha t minus 1, or the alpha t in general, is a RK k-dimensional vector. Why is it k-dimensional? Because we need to have the probability of the corresponding cluster assignment being any one of these k values. And then given this, now I can compute what is the probability of zt minus 1 given zt minus 2 and then xt minus 1. Xt minus 1, I observed it. Zt minus 2, I can go through all possible values here, and I know how to compute this term, which is already shown here. And then all I need to do is multiply that with the corresponding alpha t minus 2, or the entry in the alpha t minus 2, and then sum across all of them. Then I automatically get this alpha t minus 1. It's just a recursive computation of alpha values going from t1 all the way to t capital T. Now, this is good. This is good. So this is what we call forward computation. Now, at this point, there has to be a question how we compute alpha 0, right? So we know how to compute alpha t minus 1 from alpha t minus 2 by multiplying with the p of zt minus 1 given xt minus 1 and zt minus 2, and then sum over the zt minus 2. However, how do we actually compute alpha 0? It turned out that we can simply set alpha 0 to be a vector corresponding to mu 0, 1, mu 0, 2, all the way to mu 0k. So this is a prior distribution of the Z0 and transpose. So what we are saying is that in the forward pass, probability distribution over Z0 does not depend on anything else. That's true, right? As this graphical illustration shows us, Z0 distribution does not depend on anything. So we're going to just start from this, the prior categorical distribution. So this is what we call forward computation. And then by doing the forward computation, we can now compute these alpha t's. And then we get, of course, automatically alpha t minus 1 as well. So once that's done, we need to think about beta, right? It turned out that this backward computation is very similar. Probability of zt plus 1 given xt plus 1 all the way to x capital T. Well, what do? We again sum over zt plus 2. Now, instead of minus, we simply go for the plus, right? And then P of zt plus 1 given zt plus 2 and xt plus 1 times P of zt plus 2 given xt plus 2 all the way to x capital T. And then we again notice the same pattern here is that the beta t plus 1 can be recursively computed from beta t plus 2. So this was beta t plus 1, and then this is beta t plus 2. And then what it means is that all we need to know how to compute is this term. And then that's in fact quite relatively straightforward. Again, using the Bayes rule. We want to go into the detail, just that we don't have enough time, but I highly recommend you to read the lecture note after the lecture and then trying to derive the missing bits that I'm skipping over due to the time constraint. So log P of z t plus 1 given z t plus 2, x given x t plus 1 is going to be some constant. We always have some constant plus log of mu z, let me see, t, wait, hold on, zt plus 2 given zt plus 1 minus 1 over 2 m of zt plus 1 minus xt plus 1 squared. So this is as usual, right? So this is from the emission part. That is, what is the likely that we observe this xt plus 1? And then this comes from the fact that how likely is it for us to go from zt plus 1 to zt plus 2? And then once we know how to compute this, then it becomes relatively straightforward to recursively compute beta t's, starting from the beta capital T. But then there's a big question. What do we do if there is, how do we actually compute the beta capital T? Because there is no beta capital T plus 1. It turned out that this backward computation can be initialized simply by saying that the beta t plus 1 is going to be all one vector. And how many are there? There are k many of them. So we start from saying that, okay, everything is equally likely. We're going to simply compute what is the probability of z capital T given x capital T. And in which case, this term doesn't really matter, right? Because there's no transition going from z capital T to z capital T prime. That's why we simply say that the beta T prime is just a vector of all ones. And then we only care about this emission term. Had the z capital T been some k, what is the probability under the Gaussian distribution that we are going to observe x capital T? And then once we start from there, we apply this recursive rule over and over in order to compute beta capital T all the way to beta 1. And then once we have those two terms, then we can now compute this actual per step posterior distribution. So we're going to call it per step posterior distribution over zt relatively straightforwardly by considering alpha t minus 1, beta t plus 1, and the intermediate term that we have already shown how to compute here, starting from the joint probability. Now there's a question from John. Do you assume beta to be uniform for every recursion or just for the first recursion? Beta is never assumed to be uniform at all. In fact, we compute the beta recursively starting from the beta t plus 1, where the beta t plus 1 is simply initialized to be a vector of all ones. It's not even a distribution, the beta t plus 1 is. Because if you are a distribution, the sum has to be 1. However, in this case, the sum goes to k. So you can think of beta t plus 1 as simply a placeholder to start this whole process of recursion. So it's just a boundary condition. Now, okay, we know how to compute, let's see. We know how to compute alphas using the forward computation or the forward iteration, recursive iteration, and then we can compute betas using the backward iteration, and then now we know how to compute the per step posterior distribution over ZT. So that sounds good, okay, but that would have been enough for mixture of Gaussian, because in the case of mixture of Gaussian, all we have is this edge. That is, we need to estimate the parameters of this mean, the M functions of the Gaussian components. So that's why we need to have the posterior distribution over Z2. Then that should be fine, because we always observe the XT. However, in the case of the hidden Markov model, we need to model how the states, underlying states, change over time. That is, how does the cluster assignment from ZT minus 1 transition to the cluster assignment of ZT? And to do so, we now need to look at the posterior distribution that covers both ZT minus 1 and then ZT in order to estimate these transition probabilities. In other words, if I were to write it more succinctly, what we need to look at is the log P of ZT minus 1 and ZT. So it's not going to be just one of them, but we're going to look at a pair given X1 all the way to XT. And then I'm going to call it per pair posterior distribution. And then now let's see how we can compute this. In fact, it turned out that we can use the exactly same thing that we talked about. That is, we're going to look at the log, and then we're going to marginalize out ZT minus 1, minus 2, and then ZT plus 1. So we are looking at the ZT minus 1 and ZT, and then we know that the choice of ZT minus 1 and ZT influence ZT minus 2 and then ZT plus 1. That's why we are going to marginalize them out. And then we are going to write the probability of ZT minus 2 given X1 to XT minus 2 times P of ZT minus 1 ZT given ZT minus 2 and then ZT plus 1 and then XT minus 1 and XT times P of ZT plus 1 given XT plus 1 all the way to XT. And then these two terms, the term from the left and the term from the right, look very, very familiar to us. Why is it familiar? Because it turned out that the left term is simply alpha t minus 2 that we have just talked about how to compute in this forward computation. So it's just the alpha here, right? And then the second term is beta t plus 1, which again, we have just discussed how to compute and using a backward computation. So all we need to do, in fact, now is to try to figure out how to compute this midterm as we did for the per step posterior, because we know how to compute alphas on the forward pass and then betas in the backward pass. And how do we actually get this intermediate term is to simply look, not simply, okay, maybe I shouldn't really call it simply, because in hindsight, everything is simple, but when you're trying to go forward, it's never simple. But by looking at the log joint probability that we have written down here. So by looking at this log joint probability, what we need to do is figure out which terms contain ZT minus 1 and ZT, and then leave only those terms, and then make all the other terms just a normalization constant. And if you do that, what you end up with is log P of ZT minus 1 and ZT given zt minus 2, zt plus 1, oops, xt minus 1 and xt, this becomes some normalization constant, right? We always have that, minus 1 over 2, xt minus 1 minus m zt minus 1 squared. So we're looking at how likely xt minus 1, so our observation at the times that t minus 1 is, under the cluster assignment of the zt minus 1, plus log of mu zt minus 1 given zt minus 2, right? So we want to look at the prior over the zt minus 1 conditioned on zt minus 2, right? Zt minus 2 comes from here. And then minus 1 over 2 xt. Now we have to look at the exactly same thing at time step t, minus m zt squared plus log of mu zt given zt minus 1. And then we end up with the one final term, that is the log mu zt plus 1 given zt. Now, where does this last term come from? Is because the choice of the zt is going to influence the choice of zt plus 1. And then that's why we end up with this last term. But if you look at this, this is very much similar to the mixture of Gaussian as well as the per step posterior we looked into. So here, when we looked at, let me see, this middle term here, we derived it here as the sum, so the log of the middle term is going to be some normalization constant plus the log probability of our observation at time step t, given the fact that the zt was set to k. And then we look at what is the prior probability of zt plus 1, so that is k, given the previous time steps cluster assignment, and then how the choice of the cluster at time step t influences t plus 1. We simply now look at the 2 consecutive steps rather than a single step. So just to re-emphasize, what we need to look at is that how likely our observations of these 2 consecutive observations, xt minus 1 and xt, given the cluster assignment of these pair, which are zt minus 1 and zt. And then we need to compute the log prior over zt minus 1 and zt, given zt minus 2 and zt minus 1. Finally, we need to consider how the choice of zt influences zt plus 1. So you do see the clear analogy here. And just to re-emphasize how HMM, this hidden Markov model, is an extension of the Gaussian mixture model, going back to the middle term in the per step posterior, if there was no temporal dependencies, then what we end up with is this last term disappears, and then this log of mu k of zt minus 1 is not going to have a dependency on zt minus 1, which makes us end up with the likelihood of the observation x and the log prior of the cluster assignment k. And then that's what we would get with the mixture of Gaussian. Okay, so we now know how to compute the per pair posterior as well. So we do the forward pass, we do the backward pass, we compute those alpha 1s all the way to alpha 0 to alpha t. We compute beta t to beta 1. And then using those 2 quantities, we can compute the per pair posterior as well as the per step posterior. Once that's done, we can now do the learning or the maximization step. Where's the expectation step? We actually just completed deriving the solution to the expectation step. If you remember from the last week, the expectation step in the EM algorithm is to find the posterior distributions over the things that we had not observed. And then what we did above to derive the per pair as well as the per step posterior distributions is precisely what we need to do in order to solve the expectation step. And now we have the maximization step, that is the learning. And in this maximization step, what we need to do is, first, we need to figure out what is the emission distribution. That is, we want to maximize. So we're going to go from 1 to n. So we are going to assume that we have a n many sequences. So that's our data set. And then we're going to go from t from 1 to tn. Oops. Tn, where the capital Tn corresponds to the length of the nth sequence. And then we all know that, as we talked about, the length of the sequences may differ from one sequence to another. And then what we do is we are computing the expectation over this per step posterior distribution. So this is the posterior distribution that we computed earlier. And then over this, we compute the log joint probability, but then we only care about the ones that depend on the actual m. That is the mean of the Gaussian components. So that's why we had the negative sign here. Perhaps that's not a great idea to do. Let's actually put it here, -1/2 mzt. So we know the posterior distribution, so we can just write ct here minus xtn and square difference. So if we solve this problem, if we maximize this entire term with respect to these means, then that's how we are going to solve this maximization step for this particular emission distribution. If we were working with a mixture of Gaussian, that would have been the final thing to do. However, in our case, in the case of the hidden Markov model, we have yet another edge to consider. There is a transition. So we need to have the second step in the maximization step. That is a transition dynamics. So we're going to again write down this objective function, and then there are two summations. One summation goes from n1 to n, that is the indexing every single training or the data sequences, and then the second inner summation is going to be accessing each and every element in each of the sequences. Goes from t1 to tn. So because the length of the sequence can differ from one to another. Again, we compute the expectation this time over the per step posterior distribution. Oops. Okay, given x1n to xtn. And then in this case, we only care about that transition, right? The transition between zt-1 and zt. And then we look at all possible ways. And then that gives me log mu zt given, oops, not given, of zt-1. And then we can now maximize it with respect to all these mu k prime of k, where k prime goes from 1 to capital K, and both of them. And then again, this looks very, very similar to mixture of Gaussian, except that it's not only just each time step separately, but we have to consider pairs as well. That is, there is a temporal dynamics, meaning that this model is not going to simply assign each data point or the instance to a cluster based on how similar this instance is to the centroid of the cluster, but we also need to look at whether the previous observation, to which cluster the previous as well as the next observations were assigned to. And that's a major difference. And then that allows hidden Markov model, unlike the mixture of Gaussian, to capture the dependencies that are across time as well. So this is how we're going to solve the problem of learning, that is the expectation and maximization of the hidden Markov model. Let's say we train this hidden Markov model. So we estimated this means of the Gaussian components as well as the transition probabilities perfectly. We somehow did it. And then we did it, and then we went back to the expectation step to re-estimate all those posterior distributions. And then we came back to the maximization step to re-estimate all these parameters, and then we went back and forth until everything converged. So we have this hidden Markov model, but then the question is, what are we going to do? How are we going to use this? If you think about it, what we did with the mixture of Gaussian was after training is done, and then when the new instance came in, we simply looked at what is the cluster that has the highest log posterior probability given this observation. And then there was the assignment step. So in the case of HMM, what does the assignment step corresponds to? Because we cannot simply assign each and every data points in this sequence to the cluster independently of each other. We have to now consider which cluster each time point belongs to by considering all the other steps. So what we want is, in the inference or the test time, we want to solve this problem where Z is going to be a sequence of the observations. So that is, and then we want to find what is the sequence of assignments. So Z1 all the way to ZT, given X1 all the way to ZT, that maximizes this posterior distribution. And then we haven't really looked at how to compute this posterior distribution, but due to the time constraint, I'll just have to give you a taste of how we'll do this. And then this algorithm that I'm going to present you is a very famous algorithm called Viterbi algorithm. So how do we actually solve this? Solving this is identical, in fact, computationally equivalent to solving, finding the highest log probability, log posterior probability over this sequence ZT1 to ZT, no, Z1 to ZT. And this we can rewrite just like what we do with all those per step posterior as well as the per pair posterior. We can rewrite this by saying that, okay, let's actually remove the low. Oops, low. It turned out that in this particular case, for just writing it down for the derivation, not using low is actually easier. So we can start with the very last one. We're going to take the max of that, ZT given XT and ZT minus 1. And then how do we know this? Because we just know that the joint distribution looks like this, because joint distribution, how the joint probability looks like this. And then we know that the ZT only is influenced by ZT minus 1 and XT, right? We all know that. So what it means is that we can, in fact, we know how to set ZT in order to maximize this whole thing. And then how to set ZT to maximize the whole thing is only consider this particular transition or the posterior. And then we can do that for every ZT all the way to Z1. So in this case, we're going to look at what is the Z1 that maximizes P of Z2 given X2 and Z1. And then we now need to look at the Z0 as well. And then how we choose Z0 is to Z0 that maximizes Z1 given X1 and Z0. I ran out of space. Okay, let me move the whole thing up here times the P of Z0. So in other words, how to compute the maximum of this log probability or the posterior probability is to decompose it into all these smaller chunks and then look at how to maximize these smaller chunks. An interesting thing you notice is that these values look very, very similar to you. Right? Where did you see this? You actually saw them. Wait, hold on. I'm sorry. What? Yeah, okay. So you actually saw them at the forward computation of the forward pass and the backward pass. And in particular, if you look here, this looks very, very familiar. And then this also, where did it go? This looks very, very familiar, right? This is what we are trying to compute the max over. what it means is that we can rewrite the whole thing. I'm going to write gamma here. And then we can say that the gamma t minus 1 is going to be max of zt minus 2 log p of zt minus 1, xt minus 1, zt minus 1, plus the log of gamma t minus 2. Where does it come from? Because we notice here is that if you look here, this term, so max over z0 of the p of z1 given x1 and z0 times the p0, and then you see the same pattern, you see the same recursive pattern by looking at this whole thing, going from the, taking the max over z1. So what it means is that we can recursively compute the max of each individual component, this nested component, over and over, starting from z0. And then how we do that is to introduce this gamma. And then what this gamma does is to, when we look at the gamma of 0, what we are going to look gamma of 1. So that's the first one that we want to compute. We need to look at gamma of 0, where we come from the first term, and then we add, so we're looking at the log domain, we're going to add what is the maximum what's the max z that's going to make this. And then as we compute this gamma t minus 1, we just track what the zt minus 1 should be in order to maximize the whole thing. And then how we are going to do that is to simply record what was the zt minus 1, what was the zt minus 2, zt minus 1 that maximized the whole thing. Let me see, I think I'm missing the one, actually. Okay, so this is the zt minus 2 of the log of p of zt minus 1 given xt minus 1, zt minus 2, plus log of gamma t minus 2. So what we do is that we're going to recursively compute the max values and carry it over. But every time we compute the max value, what do we need to do? We just need to record which choice of t minus 2, so zt minus 2, led to this max value. And then we do that all the way until the last time step. And then all we need to do is just collect this recorded argmax that we have computed. And then this is called Viterbi algorithm. And then that actually allows us to find what was the optimal sequence of cluster assignment that led to this sequence of observations that we have, that is x1 to xt. So there's a question from John. Should the first term be maximized over zt minus 1? This is over zt0. So we look at the zt0, right? So why do we have to look at zt0? Is that z0 is because z0 not only influences the prior p of z0, but also influences the probability of the z1 given x1 and z0. So we have to always look at one step in the past. So here as well, this gamma, so in order to compute this gamma t minus 1, which is going to be a vector, right? K-dimensional vector, we need to look at what is the zt minus 2 that maximize the sum of the log probability of zt minus 1 given zt. Oh yeah, that's true. This is 2. Yes, I guess that's what you meant, right? So the log probability of zt minus 1 given xt minus 1 and zt minus 2 plus log of gamma t minus 2. That is the term that came from the previous time step. And then we run it over and over while recording which zt minus 2 led to maximal value. Then at the end, we just backtrack to figure out what is the most likely sequence of the cluster assignment under this posterior distribution, given this observation sequence x1 to xt. And then this is called Viterbi algorithm. And then this actually gives us a sequence of cluster assignment, unlike the mixture of Gaussian, which would have given us the most likely cluster assignment for each of the instances independently from all the others. Now, today it was pretty heavy on derivations. However, on Wednesday, you're going to see how this hidden Markov model can be useful for capturing the interesting dynamics in the temporal domain. So until last year, I actually didn't teach hidden Markov model in the Intro to Machine Learning course because it actually does involve a lot of the mathematics and then a lot of intuitions. However, I realized that it's kind of important to learn about this time series or the temporal dynamics, or at least you need to know what these things mean so that in the future, when you go into a job market and then work as a data scientist or the machine learning engineers, you should know what to look for when you're dealing with the time series data, which is much more abundant in real life than in the textbooks. So if you have any questions, you can always come to the office hour of the TAs. That's going to be tomorrow. And also you can wait until the lab session on Wednesday when Ilya and Katrina, the two TAs, are going to teach you or show you how to use HMM and in order to analyze the time series or the sequence data. And that's it for today. Enjoy the rest of the week, and we are going to meet and talk next week. And class dismissed.